AI is everywhere, right? But have you ever stopped to think about what it really means for a machine to learn? Spoiler alert, it's not magic. It's actually something surprisingly elegant. So today, we're going to peel back the layers on the secret engine that drives modern AI. Let's dive in. Yeah, we hear it all the time that these AI models, these neural networks, they have this amazing ability to learn from data. People talk about it like it's some kind of digital brain. But what's really going on under the hood? Like, what's actually happening in the code? It's not some black box of magic. It's a beautifully logical step-by-step process. And that's what we're going to unpack right now. Okay, so to make this real, let's take a look at an image. To you and me, it's obviously a cat. But a machine? It doesn't see a cat. Nope, it sees a grid of numbers. Literally just pixels. So the big question, the fundamental challenge, is how in the world does it get from this massive spreadsheet of numbers to the simple idea of cat? Well, think about it. If you want to get better at anything, first, you need to know how well you're doing, right? You need a scorecard. For a machine, that scorecard is all about measuring how wrong it is. And that brings us to our very first key concept, something called the loss function. So the first thing the network does is just take a guess. It looks at the pixels and spits out some scores for all the things it's been trained to recognize. And on this first go, whoa, the score for automobile is way up at 6.04, but the score for cat, the right answer, is only 2.9. I mean, clearly we are not off to a great start. Okay, so how do we turn that not so great feeling into a hard number? That's exactly what the loss function does. I love this analogy. Think of it as a way to measure your unhappiness with the machine's guess. If the loss is super high, you're really unhappy. The guess was terrible. If the loss is low, you're happy. It's getting close. The goal of the whole game, get that loss number as close to zero as possible. And here's the key thing. It's not just about making the cat score the highest. No, we want it to be higher than all the other scores by a nice, big, confident margin. We want the machine to be sure it's a cat, not just kind of guessing. So we crunch the numbers for our cat guess through that loss function, and boom, we get a value for our unhappiness. In this case, it's 2.9. This is huge. We now have a concrete number. We know exactly how wrong the network is. Which, of course, leads to the next big question. What are we going to do about it? Right. Knowing you're wrong is the easy part. The real magic is figuring out how to get less wrong. And that brings us to the second pillar of machine learning, optimization. And we're going to talk about the undisputed champion of optimization algorithms, gradient descent. This has one of the best analogies in all of tech. Seriously, imagine you're standing on a huge hilly landscape, and it's completely covered in thick fog. Your loss is how high up you are, your altitude. Your goal is to get to the very bottom, the lowest valley. But because of the fog, you can't see the bottom. All you can do is feel the ground right where you're standing. So what do? You feel around, find the steepest downhill direction, and you take one small step that way. That's it. That, in a nutshell, is gradient descent. And the neural network does exactly that. It calculates the steepest downhill direction. That's what a gradient is mathematically, and it takes a tiny, tiny step. Then it stops, reevaluates the slope from its new position, finds the new steepest direction, and takes another step. It just keeps doing this over and over and over, slowly but surely walking its way down this hill of error, trying to find the very bottom. But wait a minute, how does the network even know which way is downhill? I mean, our foggy hill analogy is simple, but a real neural network can have millions, sometimes billions of little knobs to turn, these things called weights. Figuring out how to tweak every single one of them to lower the final loss? That sounds impossible, right? Well, this is where the real workhorse of learning comes in. This is backpropagation. I like to think of backpropagation as a system for assigning blame. It's like a detective. It looks at the final error, and for every single one of those billions of knobs, it asks a simple question. Hey, you, if I turn you just a tiny, tiny bit, what happens to the final score? Does our unhappiness go up or down? And by how much? And the way it answers that question is just beautiful. It's this elegant chain reaction that starts at the end and works its way backward. It starts with the final loss and figures out which neurons in the last layer were most responsible. Then it goes to the layer before that and asks, okay, who was responsible for making those neurons do that? And it keeps going, layer by layer, all the way back to the very first knobs. It's like watching a ripple in a pond and tracing it backward to find the exact spot where the stone landed. Okay, quick recap. We know we need a scorecard for error, that's the loss function, and we know we need to walk downhill, that's gradient descent. But how we take those steps? Well, it turns out there are a few different ways to do it, and they each have their own quirks. Let's check out two extremes here. On one side, you've got the cautious, methodical approach, batch gradient descent. This one is super careful. It looks at the entire dataset before it dares to take a single, perfect step. The path is smooth, but man is it slow. And it can get stuck. Then you have the complete opposite, the wild child, stochastic gradient descent, or SGD. This one looks at just one example and takes a giant reckless leap. It's super fast, but its path is all over the place. But here's the crazy part. Sometimes that randomness is a good thing. It could help it jump out of a bad spot that the careful method would have gotten stuck in. And you can see that trade-off perfectly in these graphs. Take a look at the one on the left. See that orange line for SGD? It just dives down, finding a decent solution way faster than the blue batch line. But then look at the chart on the right. That's the price you pay for speed. See how jagged and chaotic that orange path is? It's noisy, it's erratic, and it never really finds the perfect, stable bottom. It's always kind of bouncing around. So what's the solution? Well, this brings us to the Goldilocks option, the one that's just right. And it's what almost everyone uses in the real world, mini-batch gradient descent. Instead of looking at everything or just one thing, it looks at a small group of examples, a mini-batch, like 32 or 64 at a time. This gives you the speed of SGD, but by averaging over a small group, it smooths out a lot of that crazy noise. And just look at the green line on that graph. It goes down fast, and it ends up at a better, lower point of error than the others. It really is the best of both worlds. All right, so let's put it all together now. We've got our scorecard, the loss function. We've got our compass for finding the way down, backpropagation. And we've got our strategy for walking, mini-batch gradient descent. When you combine these three ideas, you get the fundamental learning loop of AI. And this is it. This is the secret engine. First, the network makes a guess, predict. Second, the loss function scores just how bad that guess was, measure. Third, backpropagation figures out exactly how to adjust every knob to do better next time, find direction. Fourth, gradient descent takes that advice and makes a small update, a tiny step downhill, update. And then repeat again and again. We're talking millions, sometimes billions of times. And that's really the big secret, isn't it? When you boil it all down, machine learning isn't some single genius leap of logic. It's a surprisingly simple loop. Predict, measure, update. Just repeat it at a scale that is almost impossible for us to comprehend. And this very simple engine is what's behind AI that can see and write and create art. Which really leaves you with a pretty wild thought, right? If all of this can come from such a simple set of rules, what else is possible?